Good morning, everyone. Thank you for accompanying us to this new webinar that we are having in English for the Caribbean region. Welcome and happy Thursday. We hope that your week was wonderful and then you have a good weekend ahead of you this next few days. The topic of today is medium and high voltage cable fault location utilizing arc reflection method, understanding the ARM method and its capabilities and limitations. Thank you for accompanying us today. Um, and on the screen, you can see how our platform is working. At the left, you're going to see the cameras of the Stavometer. You can also visit underneath it. You can visit our website. In the middle, you are going to see the presentation. And at the right, please, you can send us your questions or comments during the presentation, and we are going to respond to them at the end of this session. This session will be recorded, and we invite you to visit our official website for more events, megger.com/es/events. And there you can see what other events we're having throughout the year, either online or in person. You can also request a demo on the right-hand side of our platform. And for those who attended live, you will receive a certificate of attendance. It is so good to see you and meet you all today. I am your moderator. My name is Daniela de Vacas. I'm the Regional Market Manager for LATAM. And on screen, you can see my email in case you need anything from me directly. Please feel free to contact me on my email. And also, please connect with me on LinkedIn. You can find me as Daniela de Vacas. And then you will also see some of the stuff that we're doing in the region throughout my LinkedIn, because I also share a lot of the things that we do. It is a pleasure to introduce you today to our speaker. He is Javier Ruiz. He is the cable sales manager for Mexico. And on screen also his email address in case you need it and you need to contact him directly. Javier, welcome. Thank you for being here with us today, and thank you for preparing this presentation. How are you doing today?
Good, thanks Daniela, and thanks to having me here. And it's a pleasure for me to present this webinar about fault location.
For those that are, we got a message for those that are not hearing or seeing, if at any given point you stop seeing or hearing something on the screen, please reload your browser and then you're going to be able to reconnect through everything. So Javier, the platform is all yours. Please go ahead. Thank you.
Thank you, Daniela, and thanks to all you for attending to this webinar. Okay, let's start with our presentation. First, I would like to review the agenda for this presentation. We will start seeing some considerations about cable fault location. And then I would like to review very quick the old-fashioned cable fault location method, because unfortunately we see that in some places still this old method to fault locate cables is used, and there is many disadvantages, and I would like to talk about them. Then we will continue with the cable constructions, with the medium voltage cable constructions, type of insulations, voltages, and some important parameters from the fault location point of view. And then we will continue with the modern cable fault location sequence, okay? And we will see the 4 steps of the modern fault location process. And after that, I will show you some examples of fault locations in the field. Okay, let's start with the cable fault location considerations. Of course, the objective is always to find the location of a fault in medium voltage cable, in an underground primary cable. And the challenges that we will face is to find the fault safely, quickly, and you will see that the fault location is a troubleshooting process. And depending of the fault we have in our cable is the tool we will use. Okay, so the fault location is a troubleshooting process. in which we have several tools depending on the fault we have in our cable. In this presentation, I will focus in the R reflection method. Let's say that is one of the tools we can use, but is maybe the most common and the most effective tool for fault locate cables. Next, well, you will see that the solution at the end is to apply orderly all the methods that we will mention in this presentation. Okay, talking of the old-fashioned cable fault location method, what was and what consisted? Well, first we connected a tamper, a cable fault location equipment, to a faulty cable, and we turned the voltage up to the maximum, and then we started to send high voltage pulses through the faulty cable. So when the high voltage pulse arrives to the fault in the cable, there will be arc, a flash over, and what we want to do is to walk through the root of the cable and hear where is the fault. That was the old-fashioned cable fault location process, okay? And the reason, because when we use this method, we need to increase the voltage up to the maximum, is because of the equation that we are seeing in the right. If you see, we need to hear in this method, we need to hear the fault, and we need to hear very, very clear. For that reason, we need a big bang, and if we need a big bang, we need a lot of energy. And if our tamper has a fixed capacitor, the only way to increase the energy, the only way to increase the bang, the loudness of the arc in the fault, is by increasing the voltage. Okay, so this is a disadvantage because maybe the breakdown voltage of my fault is only 2 or 3 kVs, but like I need to hear the fault, maybe I can go up to 25 or maybe up to 32 kVs in order to hear the fault. Okay, but this is not the only disadvantage. There are many, many disadvantages with the old-fashioned cable fault location method or process. Is inefficient, as I mentioned, is inefficient because if we have long cables, this method requires time and manpower in long cable runs. But the worst scenario is when we have a fault, and this fault is a short. Let's say that the fault I'm trying to find is a short between the conductor and the concentric. So if I send a high voltage pulse through the cable, there will not be a bang. There will not be noise when the pulse arrives to the fault. Why? Because we have a short. We have a short, so there is not a flashover. There is not an arc. So in this case, the worst is that I will see how my tamper charge and discharge the high voltage pulse, okay? And I will assume that in some point in my cable, I need to hear the arc, the bang of the fault, but I don't know that I have a short. And for that reason, I will spend a lot of time trying to hear a bang that doesn't exist, okay? So this is the worst scenario in this case. Also, normally when we use this process, we spend a lot of time trying to pinpoint the fault. And at the end, if we tamp the cable for many, many hours, at the end, we will damage our cable. And also, it's unsafe. It's unsafe because let's say that we are trying to find a fault, and in some segments of my cable, the concentric is corroded. So if the ground is wet and I am walking through the road of the cable, there will be a problem because maybe I will be the one that will be close the circuit when the concentric is corroded, and I will suffer a step potential, okay? So this is some of the disadvantages of this method, and for the reason we don't recommend, we don't no longer recommend this method of fault location. So how to avoid falling unknowingly in desert traps, how to avoid the desert traps? Well, the use of the TDR, okay, is very important. The TDR will be a good friend in the cable fault location process, as we will see in the next slides. Okay, so this TDR or radar is very useful in the modern fault location process. Okay, talking of the cable constructions, what we are seeing in this slide is the typical one-phase cable. Of course, we can have different materials. For instance, we have a conductor. In this case, is a conductor with wires, aluminum wires. We could have copper wires. Okay, so it could be aluminum or copper. Then we have the semicon layer of the conductor screen. Okay. Next, we have the insulation of the cable. In this case, we have EPR insulation. Most common today is the XLPE insulation, but also in some countries still we have paper insulated cables. Okay, so we have different type of insulations, and that is important for the fault location. Next, we have the insulation screen, or the second semicon layer. And then we have the metallic shield or the concentric of our cable. And finally, we will have the jacket, okay, of the cable. So this is mostly the one-phase construction of a medium voltage cable. Of course, that we can have different cable constructions. Okay, we can have different cable constructions. Starting for the left, we have the same cable I showed in the previous slide. And in the center, we have a three-phase cable. And if you see this three-phase cable, you will see that each one of the phases has its individual concentric, okay? So the way to find a fault in the first two cables is pretty much the same, because when we have a fault, the fault is going to happen between the conductor and the concentric. The same for the second cable. If we have a fault, the fault would happen between the conductor and the individual concentric of each one of the phases. But if you see the last one, the cable in the right, this one is different because we have three phases. It's a three-phase cable, but we have a common shield, a common concentric for the three phases. So in this case, we can have, of course, a fault between the conductor and the common shield or the common concentric, okay? But in this case, also we can have faults between the two conductors, okay? Or between each of the three phases or conductors in this cable. So this last cable is these constructions is very typical in the paper insulated cables. So when we have paper insulated cables and we have a common shield, we need to be aware that the fault could happen between the phases and the concentric, but also between the phases itself. Okay, so talking about the insulation, type of insulations. Okay, mainly today we have only two types of insulations. The polymeric or plastic insulations is the case of the EPR, or is the case of the XLPE. And we have also paper insulated cables. And from the point of view of the fault location, that makes a big difference, okay? Because for instance, let's say that I have a fault in an EPR or in an XLP cable, okay? Let's say that that fault is a pinhole, okay? We have a perforation in the insulation of this XLP cable. The hole will be filled with dust, maybe water, or air, okay? So when I need to do a flash over, when I need to create an arc in that fault, the voltage that I will need will be between 3 kV, 5 kV for a 15 kV cable, for instance. I will not need more than 5 or 6 kV to flash over the fault, the pinhole fault in my cable. But if I have the same fault in a paper insulated cable, for instance, if I have a pinhole in a paper insulated cable, the hole will be filled with oil, with the electric oil. And in this case, I will need more voltage and more energy to flash over the fault. Okay, so always when I have paper insulated cables, my tamper, my fault locator equipment will need more energy and more voltage to flash over faults in paper insulated cables. And this is something that we need to keep in mind when we choose a tamper or a fault locator for our facilities or for our cables. Okay. Good. So voltage and energy is what makes the difference between the two types of insulations, the polymeric or plastic insulations and the paper insulated cables. Okay, and please keep this in mind. This is a very important feature. Okay, cable voltage. When we talk of medium voltage cables, we usually say that we have 15 kV cable, or we have a 25 cable, or 35 kV cable. Okay, this is the system voltage or the face-to-face voltage. From the point of view of the fault location, what is important for me is the face to ground voltage. Okay, for instance, for a 15 kV cable, that face to neutral or face to ground voltage is 8.6 kV. For a 25 kV cable is 14.4, and for 35 kV cables is 20.2. Okay, so when I need to select a tamper for my cables, keep in mind that the voltage that I need keep in mind is the face to ground voltage, okay, of my cable. Regarding the important parameters of cable parameters for the fault location, the first one that I would like to mention is the cable capacitance. Okay, as you see, the cable is a cylindric capacitor, and the capacitance of my cable will depend of the type of insulation. Okay, the thickness of the insulation and the length of my cable. Okay. So, for instance, if I have, let's say, a 15 kV cable, and the conductor size of my cable is 500 kcm, the capacitance of my cable in 1 kilometer will be 0.3566 microfarads. Okay, if I have 2 kilometers of this cable, I will have the double of the capacitance. Okay, so the length of the cable is very important, because if I have very long cables, I will need a bigger tamper or a bigger fault locator, because there is a non-right rule that says that the tamper of the fault locator should have at least between 6 and 10 times the capacitance of my cable. So if you have a really very long cable, you will need a fault locator with a big capacitance. So this parameter is very important. Okay, if you have a very long cable, but the tamper or the fault locator that you have has not enough capacitance, you will not be able to find the fault. This is a very important parameter. The second one is the impedance of my cable. The impedance of my cable is very important. I will explain this very clear in the next slides. Okay, when we talk of TDR or reflectometry, the change of impedance is very important. But I will see the change of impedance not from a quantitative point of view, but a qualitative point of view. I will explain this later. Okay, but let's say that it's not important for me the value of the change of the impedance in my cable, Okay, a fault is a change of impedance in my cable, but I don't care about the value of that change of impedance. I care how it looks like that change of impedance. This is something that I will explain later in the presentation. The other parameter that is very important is the cable velocity or the propagation velocity of my cable. Okay, when we will see that when we are doing the prelocation with the TDR will send low voltage pulse through the cable, and we need to know the propagation velocity of the low voltage pulse. Okay, typically, the propagation velocity is about 60 or 70% of the speed of the light. Of course, we have tables in which we can see, depending of the insulation of the cable, the size of the conductor, and the voltage, we can see the different propagation velocities. Normally, all the cable, all the dampers, all the cable fault locators have an average or handle an average of the propagation velocity for all the different cables, and we have lists also in the dampers. We have a list, and we can select the correct propagation velocity for the cable in which I'm working. Okay, so this is not a big problem, but this is also a very important parameter. So, talking of typical faults or the most common faults in medium voltage cables, I will say that maybe the most common fault is the pinhole fault. It's a high resistance fault. For instance, for 15 kV cables, the breakdown voltage for a pinhole fault will be between 4 and 8 kVs. And we have continuity between the conductor and the concentric, but at some point in the cable, we have a perforation, we have a hole in the insulation, okay? So this is very, very common fault in medium voltage cables. The second fault that is very common is the burn in the clear. And this fault happen very often when we have cables with aluminum conductor. Okay, and what happened is when we have the fault, the current of the fault burns the conductor of my cable, and if we connect the fault locator from the substation, from the source side, we will need more voltage to break down, to flash over the fault from the substation or from the source side. But if we connect our tamper or fault locator uh, from the load, you will see that the voltage that you will need to break down the fault is lower. Okay, so when we have this type of faults, it's always a good advice: connect the tamper in the load side. Okay, not from the station, not from the source side. Okay, this is a good recommendation. And the last fault that I would like to mention is the short. Sometimes when we have a lot of current in the fault, the current will melt the insulation, and then will be a contact between the conductor and the concentric. Okay, this is the other typical fault in medium voltage cables. Okay, so let's now review the modern cable fault location procedure. We need to do, we have 4 steps. The first one is the safety. The safety always is very important when we handle high voltage. And you will see in the next slides that the safety is related in the cable fault location process with the connections. It's very important, the connections of the jumper to the faulty cable, in terms of the safety. Okay, the second step is the checks or the verification, in which I want to double check which one is the phase that has the fault. And also in the checks or in the verification step, I need to know what is the breakdown voltage of my fault. This is a very important information that I want to learn. What is the breakdown voltage of my fault? The third step is the prelocation. We will combine the TDR. I will explain later what is the TDR. We will combine the TDR and the R reflection method to prelocate the fault. And finally, the fourth and last step is the pinpointing of the fault. Okay, so let's review each one of these steps in the next slides. Okay, safety. Okay, of course, you need always follow the established company works rules and procedures, and you should be aware of the three sources of high voltage. The first one is the operating voltage. The second one is the induced voltage. Of course, the faulty cable is the energized, okay? But could be that we have energized cables in the same trench or in the same duct. So we need to be aware of that cables because they could induce energy voltage in my faulted cable, okay? And the last source of high voltage is the test equipment, the tamper. Okay, you could consider the tamper of the fault locator like a small substation that can generate lethal voltage. Okay, so this is something that you need to also keep in mind. So continue with the safety. As I said in the previous slides, the connection is very important. If you see the picture in the left, you will see that I have my tamper, my fault locator here, and I connect first the safety ground to this ground road. Then I connect the high voltage cable of my tamper to the conductor of the faulted cable, and the other connection is the connection to the metallic shield or the neutral of my faulted cable. Okay, and if you see in this picture, all the connections, all the neutral and ground connections are in the same road. Okay, exactly in the same ground. This is what we call single point grounding. Single point grounding. Okay, this is very important for the safety in the fault location. If you see the picture in the right, you will see that here in this case I have the safety ground connected to this road, but the metallic shield, the concentric of my faulted cable, is connected to another road. So if happens that I am in the middle, then it could happen that I will have a step, or I will suffer a step potential. This is what happens when I don't have a single point grounding. Okay, so that is very important to also to keep in mind. When you do fault location, always look for a single point grounding. The second step, as I said, it's the checks or the verification. In this second step, I want to check which one is the phase that has a fault, the faulty cable. And the second that I want to learn, or the second information I want to know, is the breakdown voltage. What is the breakdown voltage of the fault? Okay. This is very important because, for instance, if the fault I am trying to find is a short between the conductor and the concentric, I will not be able to charge the cable. I will not be able to charge a cable if the fault that has my cable is a short between the conductor and the concentric. But for instance, if I have a pinhole, a perforation in my insulation, maybe I will be able to charge the cable with 3, 4, or maybe 5 kVs. Okay, so that is very important because the breakdown voltage of the fault give me information about what type of fault has my cable. Okay, so for that reason, this step is very, very important. Once I know which cable is the faulty cable, and once I know what is the breakdown voltage of the fault, I can go with the third step. The third step, as I said, I will combine the TDR, the reflectometry, and the R reflection method. Okay, so let me explain clear of what consists this third step. The first that I will use is the TDR, the time domain reflectometer, and the TDR, the operation principle of the TDR is exactly or pretty much the same that the radar of the airports. Okay, when you have a radar in an airport, what happens is that the radar sends a pulse. The pulse reaches the plane and goes back to the radar. And what the radar measures is the time that took to the pulse go from the radar to the plane and from the plane to the radar. And if I know that time and I know the propagation velocity, okay, in this case is the velocity of the speed of the light, I will know the distance to the plane. Okay. In the case of the TDR for cables, what the TDR will do is that we'll send a low voltage, high frequency pulse, and we could say that low voltage pulse will travel through the cable with one leg in the conductor and the other leg in the concentric. Okay, and that pulse will go back to the TDR when detects a change of impedance. So in this picture that we have here, the only two change of impedance is the change of impedance at the beginning of my cable, because there is a change of impedance between the test leads of my TDR and the medium voltage cable. Okay, then we will not see any change of impedance. There is not a change in the resistance of the cable. And the second change of impedance will be at the end of the cable. Okay, that two are the only two change of impedance in this picture, at the beginning and the end. Okay, so let me explain this in the next slide. If we before to explain this, I would like to talk very quickly about how the change of impedance looks like. For instance, if I don't have any change of impedance in my cable, I will see a flat line. If I have an end, or if I am seeing the end of my cable, or the conductor is cut, or the concentric is cut, I will see an upward blip. Okay, if I see a short, for instance, a short between the conductor and the concentric, I will see a downward blip. Okay, like this one. And if we have joints or transformers in the cable, if we have joints or transformers connected to the cable, I will see a change of impedance like this one. We will see first an upward and then a downward. Okay, so this is like the change of impedance looks like in the TDR. So let's see that we have 15 kV cables. For this example, I have a 15 kV cable, and we have a pinhole fault here. This is my fault, a pinhole, a perforation in the insulation. And let's say that I have connected my fault location equipment over here. Okay, so what we will see in the TDR, what we will see in the TDR of my fault location equipment? Well, we will see first a change of impedance of at the beginning of the cable. Here, the trace is cut, but you can see that this change of impedance will be like splice, okay? Because at the end, between the tamper and the faulted cable, we have a splice, okay? So this first change of impedance will be like a splice, or will look like a splice. Then I will have nothing, pretty much a flat line. We have some noise over here, but it's pretty much a flat line. And then we will have the end of a cable, an upward blip, okay? This is what we will see in this case. And the question is, why nothing happened in the fault? Very simple. I said that this is a 15 kV cable, and this cable is has a fault, and the fault is a pinhole. Okay, this cable is faulted, but maybe to flash over this fault, I need, let's say, 6 kV. Okay, so 6 kV means 6,000 volts. When I send a low voltage pulse, let's say 15 volts, 50 volts, 50 volts, when the low voltage arrives to the fault, nothing happens. Why? Because 50 volts have not enough energy to flash over a fault of 6,000 volts. Okay, for that reason we don't see nothing over here. What I need to do is to send a high voltage pulse, and this is what I will do in the next step in the R reflection method. Okay, but what for why is important this first trace? Because this first trace shows me where my cable begins, where my cable ends. Okay, for that reason, it's very important this first step with the TDR. Okay, so let's now find the fault in this pinhole fault. Okay, so in this case, as I said, I need to combine the TDR and the R reflection method. So what the equipment or the TDR will do is that overlay two traces, the low voltage trace and the high voltage trace. Okay, so let me explain this in the next slide. We have here the same cable, 15 kV cable. We have the fault, a pinhole fault. Okay, I connect my fault locator equipment. So the first that I will have is the low voltage trace. Okay, here we have the low voltage trace. You can see here that we have the trace like looks like a splice because we have at the end a splice between the tamper and the medium voltage cable. Then we have a flat line. Okay, we don't have nothing in the fault because, as I said in the previous slide, this low voltage pulse has not enough energy to flash over the fault. So the pulse continues, nothing, flat line, and we have the end of the cable over here. Okay, now I charge the capacitor in my tamper and I release a high voltage pulse of 5 kV. When the high voltage pulse arrives to the fault, then flashover happens. We will have a flashover, an arc, and this arc, this flashover will be active during few milliseconds. Okay, few milliseconds is where the arc will be active, but that time will be good enough when the second pulse of the TDR arrives. Now we will see a short, because when we have the arc active, at the end, what we have is a short, a temporal short between the conductor and the concentric. Okay, when this arc is active, so the high voltage pulse trace will look like this one. And in this point, when both traces, the blue one and the red one, the low voltage and the high voltage trace separates, is when we have the fault. And we have prelocated the fault. Okay, so this is a very important step, because now what I need to do is to move a marker that is in my TDR and put the marker just in the point where both traces separate, and this is the point where let's say where the fault is. Okay, so once I have done this, the next step is to pinpoint the fault in this area. Okay, so before that, let me show you some real traces. Okay, you can see, for instance, in the first traces in the upper left, that even when we have a lot of noise, the point when we have the fault is very clear to see. You can see very clear here, the downward reflection and the downward blip. And for instance, in the case we have a fault at the end of the cable, as you can see very clear the separation of the low voltage trace and the high voltage trace. Okay, so some real traces that I would like to show you. Okay, once we have done with the prelocation, we can continue with the pinpointing. The prelocation, as I said, is very important because we want to learn two distances in this step. The first one is the length, the length of my cable. What is the length of the cable, the beginning and the end? And the second distance I want to learn is the distance to the fault. Okay, and in the meantime, I also get or I gain additional information, like if we have a splicer or transformers connected to the cable. Okay. Okay, once I have done with the third step, I need to do the last one, that is the pinpointing. And the reason because I always need to pinpoint the fault is because the cable doesn't run straight. Okay, we can have coils, we can have that maybe the cable goes down, then up, we have some curves. So we have different situations. For that reason, after I have prelocated my fault, always is good to pinpoint the fault. Then it's what I will do. And for in this step, what I will do is that I will do that my tamper send high voltage pulses, let's say every 10 seconds. And when the high voltage pulse arrives to the fault, I will have a flashover, I will have an arc, and the arc will generate first an electromagnetic signal and then an acoustic signal. And both signals will travel back to the damper, okay? And the first one that will arrive will be the electromagnetic signal because travels with the speed of the light. And the second one will be the acoustic signal that travels with the sound speed, okay? So in this fourth step, when the pinpointing, I will use a pinpointer. In the case of Megger, the pinpointer that we use is the Digiphone. It's a very nice tool. And for instance, what we are seeing in this picture is that the guy is trying to pinpoint the fault. And we see here this number, 66.9 milliseconds. And that means that the electromagnetic signal arrives, and 66.9 seconds later, the acoustic one arrived. So this is the difference between the arrival of both signals. Okay, so as this guy walks through to the fault, this number will be decreased. Okay, and once the guy passed the fault, the number the number will increase. Okay, so it's a very we call this thunder lightning principle. Okay, because it's like when you have a storm in the night, the first that you see is the lightning. Okay, and then you will hear the thunder. Okay, so for the reason is we call this thunder lightning principle. Okay, and once we have pinpoint the fault, we have done. We can repair our cable, we can put a joint or change that part of the cable, and that's it. We have done with the fault location process. Okay, so only to finish with the presentation, I would like to show you a real example in the field. As I said at the beginning of the presentation is focused for medium voltage cables, okay? But the fault location, the operation principle is exactly the same for fault location on high voltage cables and transmission cables, okay? And the example that I would like to show is a fault location made in a 230 kV cable. In this case, we use the biggest portable tamper we have in Megger, that is the STX40, and we use our pinpointer, the Digiphone. Okay, so let me show you this fault, this example in the field. The cable was, as I said, 230 kVs. The length of the cable was 4.5 kilometers or 2.79 miles. We had 4 splices. Okay, this is the drawing of the splice. And here you can see the lineman that connected the test leads to the transmission cable. This is the tip, some of the layers for the cable. And then here you can see the low voltage trace. As I said, we have 4 splices. You can see here 1, 2, 3. This is the 4th splice, and here is the end of the cable. This is the low voltage trace. Then we send the high voltage trace. I think that I don't remember very well, but I think that I sent a high voltage pulse of 12 kV. And then we have here, you can see the high voltage trace. Let me do a zoom. And you can hear here how both traces separate at 1.76 kilometers. Okay, so the fault has been pre-located, and now I need to pinpoint the fault. Indeed, in this case, is something that the guys asked. Please pinpoint the fault because we need to break down the highway. Okay, so I did the pinpoint with the Digiphone, and the Digiphone showed me clearly that the fault was in the second splice. Okay, so we use the Digiphone, and you can see here the technicians of the factory, the splice factory, saying the faulty splice. Okay, so this is a nice example of how to use the eye reflection method in transmission cables. Okay, well, to end this presentation, I would like to talk a little bit of some of the equipment that we have in Megger. All the units you are seeing in these slides come from Valleyforge, and we call E-Tray products. And the reason because we call E-Tray products to these locators is because all of them has the same user interface. Okay, if you learn to use the EasyTom 12 kV, you can use also the SmartTom 16 or the SmartTom 15. Okay, there is well, sorry, this is 25. Here is a mistake. It's not the SmartTom 15. It's a SmartTom 25/30. So these Valleyforge locators have the same user interface as I said, and they are very simple to use. And one of the advantages of these products is that we have a demo software, and you can practice with the demo software how to operate the units. One thing that all the fault locators in Megger have, one feature, very important feature, is the FOM feature, in which this feature will tell you if you have the same potential between the metallic shield of your cable and the ground where you have connected the safety ground of your cable of your fault locator. Okay, as I mentioned in the safeties, it's very important to have a single point, a single grounding point, and the FOM will tell you if you have the same potential between this road and this road. If the equipment detects a difference in the potential of more than 5 ohms, the FOM alert will be displayed, and then you know that you have a difference of more than 5 ohms between the safety ground of your fault locator and the concentric of your cable. Okay, and this is very important information. So this is also important. And as I said, the E-Tray products have a simulator, E-Tray demo software. You can download that demo software from the web page of Megger. And if you have an equipment, and maybe you will not have faults every day or every month, but you can practice with this E-Tray demo software how to operate completely the equipment, because as you can see, the demo software replicates each one of the buttons and features we have in the user interface. Okay, so this is a very important demo software. And here we are seeing all the portable cable fault location equipment we have in Megger, from the smaller, that is the EasyTom 12 kV. Then we have the SmartTom 16 kV for 15 kV cables. The difference between these two is the length of your cables. If you have, let's say, cables of 15 kV, and no longer than 1 kilometer, the EC thumb will be the EC thumb will be the right equipment. But if you have let's say lengths of 3 or 5 kilometers, then you can use the Smart Thumb 16. And if you have 25 or 35 kV cables, the equipment or the recommendation will be the Smart Thumb 2530. This is for cables with lengths between 3 and 4 kilometers. And the biggest and more powerful fault locator we have in Megger is the STX40. This is by far one of the powerful portable units in the market. And usually we recommend this fault locator for wind farms because the wind farms used to have very, very long cables. Okay, so that will be the biggest portable and powerful fault locator we have in Megger. If you need something with more energy, with more voltage, with more power, then we need to install the fault locators in vans. We have also that options. Please visit our page where you will see all the options for cable test vans that we have in Megger. Okay, so thank you very much for your attention, and well, this is all what I have for you guys. If you have questions, it will be my pleasure to answer them. Daniela?
Can you hear me, Javier?
Yes.
Yes. Thank you for that. It looks like we don't have any questions. You are a really good teacher here with this subject today. So if in any given case, any of you guys have any questions further down the line, you can always write Javier and ask him the questions to his email, javier.rees@megger.com. But I also, before we leave and before we continue with our day, I wanted to share with you guys I'm sorry, I'm going to share my screen with you if I can find the screen sharing button. Oh my goodness. Oh, here we go. Okay, window. Okay, so I think Javier, can you confirm that I'm sharing my LinkedIn?
Well, I'm still seeing my presentation.
On the right side on the media player, you will be able to see it.
Okay. Okay. No, but sorry.
Maybe it is working and okay, hold on. Okay. Okay, now I'm sharing the one that I want to be sharing. So I wanted to invite you guys to join our group. We have a group in LinkedIn. It's called Eventos con Megger Latam. There, I know most of the events are not in English because Latam is prominently Spanish. However, we do have interesting events and interesting events online and in person in the Caribbean region where you guys can visit us, you guys can have questions and approach us more directly. So I wanted to invite you to join our group, Eventos con Megger Latam, just like you see on your screen right here. And then you can have firsthand everything from us. So that's on my end. And we got one question. It says, what about the ICE and DEC methods?
Well, yeah, this is a very important method. In the case of the decay method, for instance, normally all the fault locators, the maximum capacitor will reach 32 kVs. Okay, so that means that we can use the R reflection method only if the breakdown voltage of the fault is below 32 kV. Okay, so if the breakdown voltage of the fault is above 32 kV, we can use the decay. The decay is, in this case, we will apply a DC high pot up to, we can use up to 40 or 80 kVs depending on the equipment, and then we can use the decay method to find faults with breakdown voltages above 32 kVs. In the case of the ice, if we have a very low resistance fault and we cannot find with the R reflection method, in some scenarios the ice is a good method to use for very low resistance faults. Okay.
Perfect. Okay, and then just at the end, please make sure you fill out our survey. Our survey let us know what subjects are of importance to you and how we can improve these webinars. Without further ado, this is all from my end. I want to thank you everyone for being here. I want to thank you, Javier, for the presentation and for your time. And I'm going to say goodbye for now, and then hope to see you all guys soon in another webinar. And also hope that you have a nice weekend.
Thank you, Daniela. Goodbye to everyone.
Thank you. I'm going to go and proceed to close the session. Have a good afternoon.